Okay, so in this video I'm going to have a look at what's called the Gaussian integral, and this is it here. I've called it I, and it's the integral from minus infinity to plus infinity of e to the power minus x squared dx, and it's actually equal to the square root of pi. Now in this video I'm just going to have a look at where this square root pi comes from. If you were to take the e to the power minus x squared, in fact, and plot it, you'll see that it looks something like this. It's our basic, our normal distribution curve. It looks like a normal distribution curve. So let's just have a look at how we can derive this. Now I'm going to start by looking at this integral I should say, this double integral from minus infinity to plus infinity, minus infinity to plus infinity of e to the power of minus x squared plus y squared. Now this is, we have two variables here, so we're going to have to integrate with respect to y and then x. So let's have a look at this. Now what I'm going to do first is just have a look at this e to the power of minus x squared plus y squared. Now that's just equal to e to the power of minus x squared minus y squared, and that as well then is just going to be equal to e to the power of minus x squared times e to the power of minus y squared by the rules of indices. So what we end up with here is just our double integral becomes the integral from minus infinity to plus infinity twice of e to the power of minus x squared e to the power of minus y squared dy dx. Okay, so let's have a look at breaking this up a little bit. Let's have a look at our inner integral first. So we're just going to have a look at this here. We'll just move that out a little bit further. So we're going to have a look at this integral here. Now we're integrating now, so we're just looking at this part here. Okay, so we're not looking at the dx here, or this part of the integral here. So this integral here in the middle is integrating with respect to y, which means this e to the power minus x squared can effectively be considered a constant. So what we can do with that, of course, is then just to bring that outside the integral. So what we end up with is e to the integral of, well, I'll write it here. The integral minus infinity to infinity e to the power of minus x squared, and then we have the integral here of e to the power of minus y squared, and we have dy dx here. Okay, now if we have a look at this then, so all I did here was just take this as a constant, and I just took it outside the integral here, so it's ended up here. Now again, if we just have a look at this integral here, again we're just looking at this part here. Now this effectively can be evaluated, so this effectively becomes a constant as well, because now we're integrating e to the power minus x squared with respect to x. So this here will become a constant, so we can effectively take this outside this integral here. So what we end up with here is the integral from minus infinity to plus infinity of e to the power of minus y squared dy, and then we have this integral here then, so we have the integral from minus infinity to plus infinity e to the power of minus x squared dx. Okay, so what we've done is we've taken our original double integral, we've just split up our e to the power of minus bracket x squared plus y squared, and then we've taken the constants individually outside the integrals, and we've ended up with this integral here. Now if you have a look at this here, this was our original integral, which is I. This was what we wanted to evaluate originally, and this here is effectively the same integral, because instead of the x here now we just have y's, but it's the same integral. So this is also I, so this whole thing just becomes I squared. Okay, so in other words, our double integral, that we started with minus infinity to plus infinity, minus infinity to plus infinity of e to the power of minus x squared plus y squared is just equal to I squared. It's equal to our original integral. Remember what we originally started with was I is equal to the integral from minus infinity to plus infinity of e to the power of minus x squared dx. This is what we want to evaluate, and we said that was equal to the square root of pi. So what we've discovered was this other double integral happens to be I squared. It happens to be this squared. So let's just have a look at this and see if we can evaluate this, see if we can do something with this that will allow us to evaluate this original integral. So now in order to do this, first thing I'm going to do is I'm just going to have a look at this e to the power of minus x squared plus y squared. Now if we actually plot this function, we'll get a 3D shape. You got to remember double integrals here. Single integrals, if you integrate something, it gives you, so if you integrate some function with respect to x here, what you're really doing is, say our function looks something like this, what you're really doing with, particularly if there are limits here, a, b, you're looking at the area underneath the curve. So if we do a single integral from a to b of some function f of x with respect to x, we get the area underneath the curve. If you do a double integral, effectively what you're doing is finding the volume underneath a 3D, some kind of 3D shape. So that's what this is here. And if we plot this, remember we've got two variables here, x and y. If we actually graph this, we get a 3D function. Now we can see here that our power here involves an x squared plus y squared, and you may recognize this as being one side of an equation for a circle. So x squared plus y squared we know is equal to r squared. Now also if we plot this particular function here, what we'll get is this kind of a shape here. So we get this 3D shape here. So you can see it from underneath here. We got your x and y axis on the flat surface here, and then we have our z axis coming up through the middle here. So if you look at it from the side, it's effectively, if you like, looks like a normal distribution curve, but it's perfectly symmetrical all the way around. And really what this is made up of, if you like, is an infinite number of circles, one on top of the other, where r is the radius, r is the distance from here out to the edge of our function here. So that would be r. And r goes from 0. So if we have an infinitesimally small circle here, our radius would be 0. And right down at the bottom here, the radius of this circle down at the very bottom here would be just infinity. So if we do a double integral of this particular function here, which is what we're doing, taking r between 0 and infinity, we would effectively be finding the volume underneath this curve. Now, I said circles there, but really what we're going to be looking at here are pipes or tubes or cylinders that have been hollowed out, if you like, and they all slot inside each other. I'll just show you what I mean in a minute, but we're going to find the volume underneath this curve. That's what this double integral is. So let's have a look at that. So we have, let me just draw it out again. We have this three-dimensional shape. I'm drawing it from the side here, if you like. Yeah. See, that doesn't look too good. Let me do that again. So we have this kind of a shape here, looking at it from the side. Now, if we take a very thin pipe, it'll probably look something like this, and come around here, and up here. So this is inside our three-dimensional dome shape, if you like. And if we take or here as being this is the radius of this particular pipe. Remember, this is hollowed out, and the edge of this pipe is infinitesimally small. So we're taking this as being our radius or. So this is our circle here, so we've got or as x squared plus y squared. Now if you look at this pipe here, you've got a height here. So our height is just going to be simply, remember this e to the power of minus x squared plus y squared is now just simply e to the power of minus or squared. We're replacing this x squared plus y squared with an or. So that should be squared there. X squared plus y squared is just or squared. So this x squared plus y squared we were replacing with this or squared. So instead of having two variables here, we now just have one variable or. So the height of this here is just going to be the function here. So that's just simply going to be e to the power of minus or squared. In other words, if you put this x or this value here into our function, you'll get this value here, which is maybe I should have the arrow pointing here. So that will give us the height of this cylinder or tube here. Now the thickness of this tube we're just going to call delta or. Delta or is the change in the radius. So if you imagine this is a hollowed out cylinder, it's going to have a certain thickness here at the edge. This red line here will have a certain thickness. Find that delta or dr, if you like. Delta or, small change in the radius. So the volume of this individual pipe here, if you were to cut it down the middle here and just open it out, you'll get a rectangle. It's just going to be length times width times thickness. So it's just our volume then. The volume of this pipe is just going to be the length, which is the length of this circle here. Remember, if we open this out, it will look something like this, let's say. So we cut it down the middle here, let's say, and just open it out, we'll get this kind of a shape here. So our dimensions, our thickness here, let's say there's a certain thickness here. This is exaggerated, of course, but our thickness here is just going to be delta or dr. The height of the actual tube here is e to the power of minus or. And our length here, the length of the tube is just going to be 2 pi or, the length of the circumference of a circle. So this is our circle here. When we open it out, we get this length along here. So if we multiply these three together here, we get e to the power of minus or squared, I should say. That should be a square there. So e to the power of minus or squared. We've got 2 pi or. This is our length along here, and then we've got our delta or. I'm going to call that dr, small change in the radius. So that's the volume of one of these. Now, if you imagine in our three-dimensional shape, our three-dimensional dome that we had earlier, an infinite number of these hollowed out pipes, these hollowed out cylinders, I should say, these with really thin thickness here, really thin edges here, they all slot inside each other. You're going to end up with an infinite number of these pipes all slotted into each other, and they make up effectively the volume of this dome shape, this three-dimensional dome shape that I showed you earlier, this one here. So you've got these pipes in here, an infinite number of these pipes in here, with radiuses that go from 0 to infinity, and all of these pipes slot inside each other so that they make up the volume underneath this curve. Okay, so what we want to do here then to find the total volume underneath this dome shape is just simply integrate from 0, we've got a 0 radius, That would be a pipe here at the very top here, if you like, and that would have a radius of 0. And then down at the bottom we would have another pipe, and that would have an infinite radius. So we've got e to the power of minus r squared, 2 pi r, and then we've got dr here as well. So now this, our original integral that we started with, this one here, effectively reduces down to this here. So it looks exactly the same, however you've got this extra r here, which is going to make a big difference. So this 2 pi here we can take outside the integral, so this just becomes 2 pi, the integral from 0 to infinity, e to the power of minus r squared dr. So this is our original integral now. This was our double integral, and then back to our single integral again that we started with. However, so I left out an r here, it should be an r here. So it looks exactly the same as the one that we started with, except you have this extra r here, which is going to make a big difference. So let's just integrate this with a little bit of substitution, I think. So let's have a look at doing this. So we have, we're going to let u here equal to the r squared. So that will give me, let's see, du dr is just 2r, or du is equal to 2r dr. Now let's just have a look at what we can do with this. Actually, I've taken this 2 outside here. I might just stick that back in again, because if I stick that back in here, I'll have a 2r dr, which is perfect. So in other words, what I'm doing here is leaving the pi outside, putting 0 to infinity here. I've got e to the power of minus r squared. I've got 2r dr. So you can see here I've already evaluated that over here, if you like. It's just du. So our integral then just simply becomes the integral from 0 to infinity, e to the power of minus u, because remember r squared we said was u, and then 2r dr we just see here is du. So it's simplifying quite well. Okay, so let's see what we can do with this one. So I just come down here now. We have, we can integrate e to the power of minus u. That's just a straightforward integral, and we get minus e to the power of minus u. Remember, we're going from 0 to infinity here, and we have our pi outside here as well, by the way. There's the pi is outside here as well, and better not forget that. It's this pi here. Okay, so let's just evaluate this then. So we have pi, actually do the other type of brackets. Now we want to put infinity in here, if you like, so we've got minus e to the power of minus infinity, and then we've got to subtract minus e to the power of 0. We've got to substitute in 0 as well, or minus 0, whichever way you want to write it. So this is what we've got to do. Let's see what happens when we do this. Now e to the power of 0 is 1, so we just end up with plus 1 here. Minus minus is plus, and this is 1. So this part here will just become, this part here will just become 1. E to the power of 0 is 1, and minus minus is plus. But what about this part here? Well, if you take, let me just do that in a different color. If you take e to the power of minus infinity, if you take e to the power of minus infinity, that's equal to 1 over e to the power of infinity. Now, really, if you raise, e is just a number. If you raise any number to the power of a very, very big number, and it's the denominator of a fraction, the fraction effectively becomes 0. So this thing here will just become 0. So what we end up with is pi times 0 plus 1. So that just gives us pi. Okay, Now remember where we started now. We remember where we started. We started way back up here where we said this here was equal to y squared, and this is what we've been doing. We've been evaluating this, and we've just discovered that all of this is just equal to pi. So in other words, if we come all the way back down again, we have I squared equal to pi. That just gives us our final solution then, where I is equal to the square root of pi. And that's it. So that gives us our what we wanted to derive. We started with I is equal to the integral from minus infinity to infinity of e to the power of minus x squared dx. We looked at a double integral which turned out to be I squared. We evaluated that and it turned out to be pi. So I squared was pi, so therefore I is just, or this integral here just turns out to be the square root of pi. Okay, so that's it for this video.